Welcome to episode 325 of CppCast, the first podcast for C++ developers by C++ developers. I'm our host, Rob Irving, joined by my special co-host, Conor Hoekstra. Conor, how are you doing today?
I'm doing fantastic. How are you doing?
Doing good. It's good to have you on here.
Yeah, thanks. Thanks for having me on.
Yeah, it's been a while since we had you on as a guest. You've been on as a guest 2 times, I think. And I believe since the last time we had you on, you have started your own podcasts, plural, right?
Yes, that is correct. So I think probably most of the people that listen to my first podcast are going to be familiar with me from that one because it has, I think, quite a bit of overlap due to C++ is our main focus. So I started a podcast with Bryce Lellback, who I think you had on just a couple episodes ago. That podcast is called ADSP, which stands for Algorithms Plus Data Structures Equals Programs. And then there's a second podcast that focuses less on C++ and more on array languages like APL and J. And that's with a panel of 4 different people. So
that's pretty cool. I'm not familiar with what you mean by array programming languages. What does that mean?
Well, very, very briefly, there was APL was a language created back in the 1960s by a guy named Ken Iverson. And it led to a very sort of niche community. It was big back in the 60s and 70s, but sort of died out. And its most popular sort of form of it exists in Python libraries like NumPy and Pandas. So those were largely inspired by array languages. So the main thing about array languages is basically there's only one data structure, and it's an array, like multi-dimensional arrays. So there's no hash maps, no, red black trees or any of that stuff. So yeah, I love it. If people are interested, they can go check it out. But I won't say more than that because that's a whole other topic.
Okay, well, I'll make sure we get links in the show notes for this episode for both of the other podcasts. Okay.
Awesome.
Cool. Well, at the top of every episode, I like to read a piece of feedback. Last week, we had Cy Brand on. We were talking mostly about Visual Studio 2022. And we got a lot of comments on Reddit. I was going to quickly read through 2 of these. One was, does IntelliSense work for modules yet? And how about for imported headers? I believe IntelliSense does work for modules in VS 2022, at least in the final release, which is coming out today as we're recording. I believe Cy did a demo of that in their CppCon talk. Yeah. And the other question was, someone's asking, is there any difference from the free community version instead of paying literally over $1,000 for the professional version of Visual Studio 2022? And for those who don't know, I think like the community edition is basically free to anyone who's like working on open source or is in like a small company. But if you work for like a larger enterprise, I think the criteria is like something like over 5 developers. You're supposed to be paying for a license. But if you just want to try something out for yourself, definitely use the community version.
Yeah, I've used both in the past, and they're both great.
Yeah, I don't think you're missing out on a whole lot of features by just using community. I think the main thing is just that, if you work for a company, that you're supposed to be using professional or enterprise. Yeah. Okay, well, we'd love to hear your thoughts about the show. You can always reach out to us on Facebook, Twitter, or email us at feedback@cppcast.com. And don't forget to leave us a review on iTunes or subscribe on YouTube. Joining us today is Gašper Ažman. Gašper is currently working on core libraries for research and trading systems. In the past, he's worked on large-scale distributed systems such as the Amazon retail search engine. He's a member of the British Standards Institute C++ delegation and has been a part of the C++ committee since 2017. He's fixed some proofs in Stepanov's From Mathematics to Generic Programming, published C++, The Beast is Back with John Kolb, spoken at C++ Now, and is an author of Using Enum, which is a C++ 20 paper, Deducing This, the ordering customization points in C++ 20, and is currently working on contracts for C++ 26. He lives in the gothest part of London, next to the magnificent Abney Park Cemetery, and is friend to crows. Gašper, welcome to the show.
Greetings.
All right.
Yeah, that was honestly the longest bio that I've ever had.
I'm supposed to ask the Jason Turner follow-up question about the bio, but I'm actually going to ask something that's not in the bio that I just happen to know about you that I am very, very jealous of. You're one of the few people that I know sort of in my age bracket that got to work with Alexander Stepanov, correct?
Yeah, I did. I worked with him for 2 years while I was in Dublin. I got to go to Palo Alto quite a bit and worked with him. I was at the infamous Palo Alto meeting.
Oh, wow.
Of the concept proposal, where Sean Parent came to visit Alex, and they talked about how to structure concepts so that it won't suck, and we all know the history of that one. They do not suck. Mostly. We actually wrote quite a bit of like pseudocode at that particular meeting. That was really fun. I mean, obviously, like I was like super junior and did, all of the, well, not all of it, some of the grunt work of coming up with examples for the grand minds meeting in the biggest meeting room of our Palo Alto office when I was at A9. But I got to learn a lot, which was great. And then after I actually moved to Palo Alto to be closer to the mothership, as it were, I actually, like I spoke with him quite a bit. Like I went up to his office, a lot, and like just talked about stuff. He actually interviewed me for A9, which was super fun.
Wow.
Like it was a 3-hour interview, which started with me asking him what he thinks of ranges. As implemented in D, and he muttered something I won't report. And we ended at Old Church Slavonic and how you dry prosciutto. Like it was actually really, really like an all around cool interview. Like it's probably the coolest interview I've ever had. Yeah, it was fun.
Yeah, I'm very, very jealous of that opportunity. It's not once in a lifetime, but I don't think, Stepanov isn't working anymore. So it's something that, I would have loved to have the opportunity, but I'm very jealous of you.
But thank you. I'd be jealous of me, honestly. Like,
I was just going to pause real quick. It just got quieter, Gašper, but I could hear like a little noise.
Maybe?
And I was wondering if you knew what that might be.
I don't know what the noise would be, honestly. Well,
did you hear that too, Conor?
It sounds okay on my
It sounds
end.
okay now, but I heard this. I don't know how to describe it. It's not like static, but okay. It seems to have gone away now. So we'll move on. Okay,
right.
So Gašper, we got a couple news articles to discuss. Feel free to comment on any of these, and we'll start talking more about the deducing this proposal and maybe some of the other work you've done. Okay.
Mm-hmm.
So this first one is a new website, cppbyexample.com. And just a new resource for looking at examples of how to do various things in C++. It seems to be pretty well put together. I looked at the About page, and the author was saying how they're choosing to only cover the previous version of C++. So currently all the examples here are C++ 17, and they plan on adding C++ 20 examples once 23 gets published.
Yeah, I took a look through some of the examples, and they're super nice and concise. Like I really like that. I really disagree with the Const West style, but I'll survive that one. The last thing that I think about this is something they really should fix. It suffers from the problem. If you've ever had a really large library of music, like have the band start with the. And so music programs have started ignoring that as a stop word in alphabetical sorts. And this one has a similar problem with how to.
How to, yeah.
They should really just ignore it in the alphabetical sorting of examples. But other than that, I think it's an excellent compilation of just things that the newcomers to the language get stuck on. And it's an unsticker. I love it. It's a great project.
Definitely.
Yeah, I took a look as well. I agree. It's a great resource. I wish it had included the C++ 20 stuff, because there was a couple times, like specifically when they're talking about looking things up in containers, like there's the new contains method that it's very sad not to see that, because it's like explicitly what a couple times in the code examples is used for. And then another thing that stood out was the entry how to add to an array. And I was like, like that's not possible because a std array is literally fixed size. But then immediately when you click on that, they say, oh, if that's not possible, you have to choose a vector, which it's interesting that that's like they didn't make a mistake there, but they still left the title as it is. I guess maybe array is known as non-fixed size in other programming languages. But overall, it was, I think, pretty great.
Honestly, I think that's a really, really great thing that they did, because the way everyone will navigate this page is by Control F. And at that point, the title has to have what Control F will find.
That's true. Okay, next thing we have, you mentioned Timur Dumler a few moments ago, I think. This is his trip report for CppCon 2021. He has joined, I think rejoined, JetBrains now as a developer advocate, and he was giving his perspective as an in-person conference attendee. I think I did a trip report, a red trip report last week that was from one of the virtual attendees. Did either of you make it in person to CppCon this year?
No, I couldn't have if I wanted to. Yeah, Timur has some very useful workarounds for being able to fly there this year from Europe.
Oh, okay.
I did not attend either, neither virtually or in person. I heard great things about it, and also too, I'm not sure. Do either of you know what JetBrains does? Because like previously, they just used to release the talks on YouTube, but now they're released through like a third-party site with like private links, and I don't actually know. So maybe JetBrains can. I'm sure there's someone from JetBrains listening to this right now, and they can tweet. Like, do they all get released at the same schedule and just through a different portal with private links? Or
I didn't realize it was JetBrains releasing this. You're talking about the CppCon 2021 videos?
Yeah. So I think since maybe last year as well, like JetBrains has a new sponsorship deal somehow that for a certain period of time, they don't get publicly listed. It still all goes through the CppCon YouTube channel, but like that's how I consume all my online talks. It's just through YouTube. But now I think JetBrains has some sort of mechanism where they list them privately and get the links, and then they do it through some portal. But I can never figure that out. Like, so JetBrains, add us and let the community know, how do we watch these talks?
Yeah, I mean, I know the keynotes I believe have all been published, and I saw links on Reddit. But you're right. I'm looking at the CppCon YouTube page right now, and I don't see any listings for 2021, but I know they're out there.
Yeah, exactly. Yeah, I think the most recent one is from 3 months ago and is not a 2021 video. So
interesting. Okay, yeah, we should definitely figure this out and let listeners know the best way to find the CppCon content that's already up there. And I'm sure the rest of the videos will be coming soon. Usually, I think it takes a couple weeks to get all of them out, but they get the keynotes right away.
Yep.
Yeah, I was really hoping I could watch Ben Dean's talk on Deducing This before this interview, honestly, to like crib off his notes.
So if you're an avid talk watcher, and this is why I was so curious about the JetBrains situation, is I happen to know that Ben Dean gave a version of that talk at the North Denver C++ meetup, and if you know their YouTube channel, it's very small, it's only got like 86 subscribers. There is actually a version of it online right now. We can link it in the show notes. So, yeah, I'm not sure when that's coming out. He gave it at CppCon. I'm sure it'll be the same talk. But there is a version that exists online somewhere if you know where to look.
Very cool. Okay, and then the last thing we have is this is a blog post about how to learn compilers, LLVM edition. And it's just a good collection of links for anyone who wants to get started in understanding how to, get into compiler development. These are a bunch of like shorter articles and videos that you could watch instead of reading maybe a huge book, depending on what your style of learning is. Seems like a good resource. I know this is not something I'm looking to do myself, get into compiler development. Either of you have any interest in this stuff?
Yeah. So it is a really surprisingly comprehensive, very short list for the really, really enormously broad topic that it covers. like having written some compilers myself, although nothing as fancy as LLVM.
Sure.
It is pretty much the starting point for every part of the compiler.
They have broken it down by like front end versus back end. So if you're only interested in either of those, you could just focus on reading those resources.
Yeah, but the mid end is where all the complexity is. Like, sure, front ends are complicated, but usually they're well specified. The mid end is dark magic.
I feel like we haven't really discussed the mid end. What exactly happens in the mid end?
Well, so the front end gets you the initial intermediate representation, right? Like it takes the C++ or the Rust or the C or the Ada or, you know, whatever the hell human readable mumbo jumbo you have, and turns it into something that university professors understand, which is, you know, a more symbolic representation. And the reason you want it in a symbolic representation is because all of this fancy research into compiler optimizations, which are also known as semantics preserving transformations on programs, basically you need to have a representation that can represent both what the language, like the person writing in the human readable language meant, and what the CPU can swallow on the other end, which is what the backend chews on. And then most of the transformations actually work on the middle end that take it from, you know, one way of representing the program to a much more streamlined and hopefully faster to execute way of representing the program. This is where you do loop unrolling and you know, inlining and all of those fun transformations that eliminate a whole lot of work, such as, you know, not computing values that never get used, figuring out that you can transform a whole loop into a recursive equation that then gets executed in a finite number of steps. All of that stuff is done in the middle end because all of these optimization passes work on the same language. And then you give it to the backend thing that really, like, mostly just takes the intermediate representation if it's rich enough, and in LLVM it is rich enough, and makes it into native code assembly. And then there's a few peephole optimization passes to like really fine tune what, like, the output to whatever platform you're running on. But all of the really fancy stuff happens before that.
Interesting. Thank you.
I can also second. This is a great, super short, comprehensive list. I mean, I've heard of probably half of this stuff and half of it haven't. In the general intro section, there's a free Alex Aiken course. He's a prof at Stanford on compilers that I worked through while I was at Amazon, and it's a great resource. And I haven't worked through this one personally, but the backend resource from NAND to Tetris is a pretty well-known resource that I have a couple friends that have gone through, and they say it's fantastic because you basically go from like nothing to building up a Tetris game. So you end up with a really, really comprehensive I mean, if you go through the whole thing and don't give up, you end up with a really comprehensive understanding of like every level, which is great.
Very cool. All right, so Gašper, I know we've mentioned the Deducing This proposal before on the show. I don't think we've ever gone into it in any depth. And I don't know if you remember this, but I think like 3 years ago at CppCon, when it was still being held in Seattle, Jason and I and yourself and a couple other attendees and speakers, I think, went to dinner. And I remember you speaking very passionately about deducing this, and it was kind of just like whoosh over my head. So I was hoping you could maybe start off by giving like a high level explanation of what the deducing this proposal is.
Oh, I'll do you one better. Later on, I'll regale you with the story of how before that dinner, me and Ben Dean went to lunch and came up with the whole thing.
So that's when he started getting on. Okay. interesting.
Yeah. But to explain the proposal first, and at this point, I kind of want to stop calling it a proposal because it is a C++23 feature, unless a national body objects at the last minute to actually passing the standard, which won't happen because there's no actual serious objections to the feature. So yes, there is a procedural step still that could be invoked, but it won't. Right. So in the end, right, like member functions are functions, and functions have parameters. And when you call a function, you supply arguments to match those parameters, and then the body of the function gets executed with the arguments, having the names that have been matched. That's broadly true of every function call ever. And for member functions, there is a parameter that behaves sort of weirdly, which is the object parameter. It, at this point, up until this one in C++, had this weird name, this. That's why we call it the implicit object parameter. It is there whether you like it or not. If you don't like it, you need to mark the function as static, and then it behaves totally differently, right? And when you have an expression called like x.foo, paren, then that x gets matched to the implicit object parameter, becomes the object argument, and then the body of the member function gets executed. So deducing this is really just a way to say, to mark one of the parameters to the function, in this case, the first one, as the object parameter. So this is the one that you match the object argument to, instead of matching it to the implicit object argument. That's it. Like, and in practice, what this means is that instead of writing foo without arguments, you say this, my class name, self, as the first argument, and that's it. Like that function will now have a body where self refers to the x instead of this referring to the x. And you can't use this inside that function anymore for various reasons, which we can get into later if we want to. But yeah, that's really it. You designate one of the parameters to the function as the object argument, and that's how matching happens for that function. Now, that seems like a pretty minor change, and it is, but it leads to a large number of places because since you can now have a place to name the argument, you also have a place where you can write the type of that argument. Before, the type was implicit because it was given by the class that the member function was contained in, right? But now we can write the type, and we can be boring and write the same type and then put our ref next to it, and then everything happens the way it used to, and it's all fine. We could write the qualifiers for the implicit object parameter before in C++20, for instance. You put them behind the parameter list for the member function, right? That's what the const ref after the parameter list looks like. That's really the qualifiers for the implicit object parameter, right? So now we can just write the qualifiers right there in situ, where they belong realistically. That's why you can't write them redundantly at the end anymore. If you have this parameter, let's say. And because you can name the type, if you make the member function a member function template, you can now deduce the type using normal language rules. Nothing surprising there. But this turns out to be a huge, huge deal. For instance, if you are in a base class, if this is a member function of a base class, member function template, I should say, and you are calling the member function on derived, the deduce type, just like for any other parameter, is going to be the derived one, which means we don't need the curiously recurrent template pattern anymore. This suddenly takes mix-ins from being a language feature that you need to understand templates to understand, to anyone can write this, and it just works the way you'd expect. You don't even need to write template anymore, because since C++20, we have auto parameters, right? So if you just say this auto ref self, that's it. That's all you need to do. Self now behaves pretty much the way it would in Python. Hooray. It gets better because you can concept qualify that auto, right? Mm-hmm. Which means this member function only works for derived classes that also model this concept. And you can constrain your mixins that way. And it'll just work the way it's supposed to. Like it does what you want it to do, basically, and it doesn't read weird, which is, like, I don't know, I just find it great. It's really useful for also every place that you needed to perfect forward the object parameter. Like the classic example for this is implementing, the get method of optional, or the star member function of optional, like the star operator, the dereferenced operator. Mm-hmm. Because you need to perfect forward the return value qualifiers to the actual value that you contain. And this is actually a lot more common than people think. Like every time you're forwarding a member function call to a data member of your class, you should be perfect forwarding the reference qualifier. Like for instance, stud vectors front and back should really be overload sets that had 4 different overloads. They're not, but they should be. Because if your vector is an R value, like going out of scope, why shouldn't you move out of the first parameter, right? Sorry, why shouldn't you move out of the dot first? And the same should be true of any accessor to vector. Like if your vector is an R value and you only need that one element, please move out of it. That should just be done if you're forwarding something. Even if you have some kind of a callback, which is another whole topic, and you're scheduling a part of that callback to happen again. Like you have a data member that needs to, like you have some string that you need to log or something, and you're not going to need anymore. You should be moving that string into your logger callback or whatever. But what if your callback doesn't know if it's going to be called again? Well, if it's being called as an R value, it's not going to be called again. You can be pretty sure that it's going to go out of scope after the operator parens finishes. But if it's called as an L value, it very well could be called again. And in that case, you have to copy. That was actually the original motivation for this paper, because in Lambdas, you cannot actually do that, right? Like in Lambdas, you don't get qualifiers on your call operator, which means you cannot distinguish whether a Lambda is being called as an L or as an R value. And I can get back to that later when we're at the story. So if you think about it, like again, and this gets us to recursive lambdas, a lambda really is just the closure object with the function that you write in the code being the operator parens of that closure object. And really that's how they're specified, that's how they're implemented, that's how they work. Which means that if you supply this auto-ref self parameter to the lambda, you can now add the closure object itself. Now, you still can't refer to members because they don't have defined names, and they might not even be there. Like, that's a whole thing. But there are a few things that the lambda itself does support. For instance, calling it. kind of obvious that you should be able to call a lambda. So you can call the lambda recursively. Another thing lambdas support is moving them, right? Lambdas are movable. Some of them are copyable, or rather copy constructible. They're not copy assignable, so they're not copyable. But they are copy and move constructible, which means, let's say your lambda is a callback. Your closure object is holding some resources that the callback needs. And let's say your callback gets called. It's currently being owned by the execution system that it's residing on. And it figures out that it actually needs to be called again. Either not all of your input has arrived yet, and you need to be called again on the remainder, or maybe the timer has expired too early, and you need to reschedule the timer to be called again once the event actually happens, or whatever. Maybe your connection's not dropped yet. Fine. Up until now, you couldn't make the decision of, do I just return and not reschedule myself, or do I reschedule myself from within the body of that lambda? Because the lifetime management of your callback system wouldn't be able to handle that. But now that you can get in the body of the lambda, you can just call schedule again, move the closure object into the schedule call. So you move construct it again into the queue or whatever your schedule system is using, and let the current closure always get cleaned up. Done. No more design space there. You can streamline a whole bunch of branches. Like it basically gives you the design space back for the lifetime management. And this didn't used to be ergonomic, so people didn't do it. Like they had additional restrictions, like you needed to return a Boolean, like, yes, I want to be cleaned up, or no, I do not want to be cleaned up, or whatever from the call, right? Now there's no need to do that. Like my homegrown scheduler actually has a Y Combinator built in because they didn't want to make people return a Boolean. So basically, when you write a lambda, you get your own object as the first parameter so that you can construct yourself into the next call if you want to. But like, people don't understand what a Y Combinator is, number one. So the ergonomics of that are somewhat doubtful without deducing this. And it also takes a whole lot of template metaprogramming to do correctly. So I'd rather not do all of that,
I love combinators, but yeah, the Y Combinator is it's I think Vittorio has a pretty good blog explaining it. But yeah, not my favorite combinator, although it is a cute trick to show the lambda and C++ using a Y Combinator. But ideally, there's a better solution, and it's showing up in C++ 23.
Yeah, exactly. We don't need the Y Combinator anymore. We have it built into the language, and it doesn't read like Y.
Yep.
Because Y is the appropriate response to seeing a Y Combinator in code. Right. There's another really, really cool consequence that only showed up with coroutines. Like coroutines of free functions work well enough. Like the one thing with coroutines is that you should really be taking all of their arguments by value, because you need to ensure that they survive until the coroutine exit, right? And if you're writing a generic coroutine, that means you can't rely on the environment ensuring that, which like leads to a lot more pitfalls for dangling things, and it's like super annoying. So taking things by value by default with coroutines, probably a thing you should do. Unfortunately, there used to be one parameter in the language that you couldn't take by value, and that's the implicit object parameter. Like, it's always a pointer. With deducing this, if you don't write the ref at the end of your type, it's not a reference. It's you take your object parameter by value, because that's what the language says happens. That's what that's what it looks like. That's what happens. Which means that you can now safely write coroutines as member functions.
Okay.
and you're not going to leak your objects.
Yeah, that's really nice.
Right. It is really cool. And that is something we didn't foresee because coroutines weren't a thing when we were designing this. And it just so happens that it solves that too, which, is true of any good proposal. Like, it integrates with the rest of the language so seamlessly that you're like, why the hell wasn't this before? So to sum all of that up, though, deducing this makes member functions as powerful as free functions, but keeps the nice syntax of member function calls. And that's really it. Like, there's no other weirdness. We just unified a bunch of the parts of the language, and now they're no longer annoying to use.
Sounds awesome. Do you want to talk some more about the original inspiration when you started working on deducing this?
Right, yeah. So it was CppCon 2017, and I was young and happy, and I was at CppCon. I was meeting all of the cool people, and I had met Ben Dean a few years before, and we caught up in the hallway after. I think it was Alexandrescu's keynote or something. It was something like that. Like, we were in the hallway. We wanted to go to lunch, and he said, what's really bothering me these days? I can't know from a lambda whether I'm being called for the last time, because I'm returning a bunch of things, and I want to know if I can return them by move, or do I have to return by value, which would copy, and it's inefficient, and I just, like, it really grinds my gears, basically. Ben is like that. He wants everything to be perfect.
Mm-hmm.
And I said, like, if you could figure out the qualification of the lambda function call, then you'd be able to do that, because you'd just be called as an R value, and it really is the R value. Sorry, it's the R valueness of the closure object, isn't it? Like, that's really what we're. What if you were able to just get? What if you were able to name your closure object? That I remember having this epiphany when I walked right through the door of the Maidenbauer Center, where CppCon used to be. And that's when it clicked. Like, yeah, of course, you should just be able to name your this parameter and know the qualifiers on it. And then we sort of hashed out the syntax at lunch. And it wasn't the current syntax. It was worse. And then we had a few more dinners with some other people. And yeah, that's how we arrived at, we should write a paper. So we did. And then we shopped it around. And I, for the life of me, couldn't find who. Said, you know what? Barry and Cy Brand are writing pretty much the same paper. And I said, they are? Let's get in touch. So I get in touch with Barry over Twitter. As we all know, all committee business is done on Twitter. And turns out they started from a completely different place. Like, they didn't start with the value category of lambdas and recursive lambdas. They started with optional, and how annoying it is to have to write 4 overloads of freaking every member function of optional, especially since Cy was already working on monadic optional and .then, and all of those maps and things like that need all the forwarding in order to be correct. And so it was just a mess, right? And not only was it a mess, it compiled slower because you needed to forward to another free function that implemented your logic so that you could prove it, and then just do the casts. And if you use std forward, that's more function instantiations, and it's horrible at debug time because you have to jump like in a debugger, you have to jump through all of the std forwards, which is amazing. um, and so on. So Sai was really pissed about optional, and I was really pissed off about lambdas because, like, by the way, all the committee proposals start because somebody's pissed off about something. We're a very angry bunch of people, and that's why we do a whole bunch of work over years. The anger does not subside until the work is done. Yeah. So anyway, they had a different syntax in mind because they started from a different place, and so it ended up that we went with the syntax that me and Ben were proposing in our paper. We ended up using their paper number, and then there was the whole saga of how do we get this through the committee. So when we first merged the papers, Barry was planning to present it at EWG, and we shopped it around a bit, and there was a lot of resistance.
What committee meeting was this at? Do you remember?
Oh God, no.
Do you know what year it was?
2017, 2018.
Well, it would have been 2018, but I think it happened after my C++ Now talk. Because once we wrote the paper, we realized that there was a lot of resistance, and we didn't even present it. Like it was just like, oh, this is new novel syntax, and people are like, why are you doing this? This seems like it's not useful or something. And I said, okay, wait until C++ Now. Let me present this. Let me actually have like a proper hour, like, what was it, 3 hours? Or was it, no, it was an hour and a half that went over by like half an hour. And the C++ Now crowd loves to hackle, which is great because you iron out all of the problems with proposals that way. And so we had this extended presentation at C++ Now where I not only presented the paper, but like 4 different extensions that we're planning and why the syntax needs to be the way that it is, and so on and so on and so on. And we ironed out quite a few problems, and we were able to actually listen to people's issues with it throughout the week of C++ Now. Like, it ended up being a really great time to iron out things and to also to socialize the proposal. And the reason you need to socialize novel syntax, I find, is because committee people are still people, and human brains do not like change. And we're always like, oh, there's another thing I have to learn. Like, why? Why are you doing this to me? I don't need it. But it turns out that when you present something, and then 3 months later, a person sees the same thing, recognition turns out to be a really positive emotion. And so people, when they saw it again, were like, oh yeah, I've seen this, I understand this. Mm-hmm. And it's a neat feature. I kind of like this. And so I kind of like this went in several waves throughout the committee. And it's really funny how every single person seeing this paper comes up with the same objections at first. And when you explain to them what the problem is with, the alternative proposition that they're making, they're like, oh, but this. And it's one out of the 2 predictable things. And then you just work through the graph to the same place where we ended up. And the funniest thing is, that's where we started, like the paper authors. That's literally where we started. So when this was first presented at EWG, they did not like it. So we presented it again with, having done more research. Like, the committee's always happy to approve more work, right? So we did more work. We presented it again. There were 4 syntaxes in that second iteration. And the committee, the EWG, had a poll about which one they liked the most after the presentation, and predictably picked the wrong one. And so then all of us 4 authors went, oh my God, why? Okay, we're now working on a paper where we don't like where it's going. This is not what we signed up for. but let's just write it like it's better than nothing. Fine, like EWG wants it that way. Let's do it that way. And we did it that way, and it was like wrong. It was so wrong that we were like, no, we need to somehow reverse this. Fast forward to CppCon the next year. That was now 2018 CppCon, I think. Okay. The start just went pretty quickly, I think. And I stop Herb Sutter in the hallway. He is the committee convener, for anyone who doesn't know. Also really an amazing mind. And I explained to him the issues, and he predictably comes back with the same graph of things that I've already talked about. And we walk through the graph in an hour and a half, which, to his credit, that's incredibly quick. To get through all of the phases of deducing this design. And he says, yes, I see EWG really did make a mistake. I believe that this can be reversed. Why don't you talk to Ville, who used to be the chair of EWG at the time, and figure this out? So I take Ville to lunch. Fortunately, this is CppCon. Everybody's there, and it's not a committee meeting, so everybody has time, which is great. So over eating a sandwich, I explained to Ville what happened and ask him what we can do about this, because this is going the wrong way. And we have polls from EWG, and he said, Gašper, don't worry. This is material new information. Write that into your paper. Present the syntax as you want it to be, and I'll schedule it. It's good. So we get rescheduled with material new information, which basically was just, y'all are wrong, please reconsider. And they did. So after that, we were basically clear of EWG, but because the paper had changed so many times, everybody was super scared about passing, something that wasn't properly vetted and didn't have an implementation. And there were issues that turned out not to be substantiated over the implementability of the recursive lambda part. There used to be a recursive lambda proposal that was an alternative to this one. Turns out it wasn't implementable for various reasons, but the main one is in the other recursive lambda proposal, which gave the lambda object a name outside of the parameter list. You couldn't do size of the closure inside the lambda body because that turned out to not be computable without solving the halting problem. Turns out with deducing this, you can't actually name the type of the lambda inside the parameter list because it always has to be a template. But the other proposal, it could be a normal function. So with deducing this, it always has to be a function template because the lambda body isn't formed. There's no way to get decl type of it at that point, right? So there's literally no syntax you can use to define the type of the lambda, which means the size of expression is dependent and everything magically works. So it took me another few months to CPP now the next year to sit down with David van der Voorde and explain to him how that works. And then at that point, he had enough information to say, yes, I believe this is implementable. And then Barry sat down with him a few months later and implemented it in EDG, the EDG compiler. And so with the implementability of Lambda issue solved, we got seen by EWG again, and they approved it. But said, you know what, like we're still uneasy about this, like, eh. And then we got seen by EWG again the next meeting saying, we have nothing more to say, really, like nothing happened in these 3 months. We did some more research, it all works. We've got wording. So should we just send this to core? And EWG sent it to core. And yeah, a few votes later, here we are in C++23.
It's interesting.
It was a saga.
Yeah, it's interesting because I primarily sit in a library, and so I don't often sit in language, even though it's all virtual now, so it's whatever, just sitting in your own apartment. But my view, and this might be biased because I speak to Ben quite a bit, is that there was like the Deducing This paper, at least towards the end, had like pretty good consensus, and like it was one of the least controversial because of how well it played with all the other, like it's very rare to have a new language, like something on the language side that just works with almost all the other existing language things. And because of that, there wasn't too much controversy about this getting in, but it sounds like that is not the way it started. That it was a long uphill battle for what ended up being, or I don't know, is it still controversial at this point, or
no, not at all, not even
mistaken?
close.
Okay, yeah. So
it got consensus, but it took years. It got years for people to get familiar and comfortable with the original design, basically.
Interesting.
So, which is not how most paper goes. Like most papers go through a lot of iterations where there's tweaking and so on. This paper pretty much got born and then elaborated until all the FUD was gone. FUD being fear, uncertainty, and doubt for people who aren't familiar with the term.
So what are like the top things, developers should know when C++ 23 comes? Like, how will deducing this make their lives simpler? Like, is it, the CRTP pattern is just kind of going to go away and you can write that type of code a lot simpler? Like, what kind of things should we highlight?
I think that it really depends on what kind of code you're writing.
Okay.
Like for me, the code that I write, like 20% of my code base is just gone. Because it's mostly forwarding through various layers and like simple program transformations that have so much forwarding and forwarding and forwarding and forwarding. I did a quick survey before the show, and actually half of my function calls are going to be gone because I don't have to forward through an additional layer anymore, even. So it'll compile way faster. There's no more overload resolution between 4 alternatives anymore, so it'll also compile way faster.
And also not having to write that is like a huge win.
Yeah, like it's a huge win. But I write domain-specific languages, right? Like I write libraries that connect various components together. Like specifically this year, I've been writing log-free schedulers. And that's all about, shaving off every cycle you can through inlining. And turns out that forwarding is a really good way to inline things, because the compiler sees that, yep, this expression really is type identical to that other one, and it has the same pointer. Done, right? That's not true for a lot of my colleagues who don't write function templates all that often. And for them, not a whole lot is going to change.
Okay.
For people who write a lot of type erasure, things get really interesting because of by-value parameters. Because you suddenly don't have to erase 4 overloads. You erase the by-value one and expect the language to move. And that allows erasing factories that basically wasn't ergonomically possible before. Like, and that's why nobody did it. Like, there's a whole lot of things you could do in configuration that you couldn't before, like just because the code ended up being so horrible. But yeah, other than like giant code reductions, it doesn't enable a whole lot of things. But because it makes so many things that we used to do a lot easier, I think that there's going to be a lot of emerging patterns built on top of this that we just didn't, like, some of us did them in spite of the language because we had to. But I think a lot of these advanced quote unquote patterns that we used to leave to the library authors where speed was important, we will just expect normal everyday programmers to just use because they're now nice, right? They're no longer horrible hacks, effectively. So I think that it'll streamline that, but it won't change. I mean, it might change the paradigm down the line when people adopt the new idioms, but who knows? Idioms are always emergent.
for folks that are interested too, on top of Ben Dean's talk that'll be on CppCon and it's on the other YouTube channel, the paper itself is littered with like before and after or Tony tables or whatever we call them. So if they're curious of what the difference is, like a ton of it is like, you know, it's like a fraction. The after table is a fraction of what it is on the left. Yeah, it looks awesome.
Very cool. We're running a little bit low on time, but I did want to quickly ask you, you're also one of the authors on defining contracts, and I wanted to ask kind of how is that paper progressing? Do we think we're going to be getting contracts back in the language after it was dropped from C++ 20?
Right. So defining contracts is not going to progress anywhere because it's a let's agree on definitions paper. So it's an FYI and not a design.
Okay.
But I'm also a co-authored on the closure-based syntax for contracts proposal. I'm also a co-author on the MVP for contracts proposal. So those are probably better ones to cite. The numbers are P2463 and P2388.
So put those in the show notes.
What happened there is that contracts were not baked for C++ 20, and we took them out. And ever since, we've sort of been figuring out in the contract study group what the minimal viable product looks like, because we don't want to ship everything that anyone could possibly want in, the P0. We think that we have agreement on what semantic features need to be there. But it turns out that a lot of people dislike the attribute-based syntax that the original C++ 20 proposal used. And that's for various reasons, not least because it looks like attributes. Contracts are this really surprise pedantic design space. Because we also put them into places that are shared with C, that is headers. And so we actually need not to design just for C++. We need to design something that C is going to want to use in roughly the same fashion as well, if we can. And with C, it turns out that where the contract proposal currently puts those things is in the attribute space that applies to the function type and not to the function definition. And contracts don't really apply to the function type. They apply to the function that you're defining, right? And so they're in the wrong place if they're an attribute. There are worries that will cause confusion. I have other worries about that syntax, and it's just very constrained for what else we wanted to do. For instance, there's no way to, there's no nice way to really express a closure in that syntax. And fundamentally, a contract checked in a post condition is a closure, right? You construct the closure at function entry, and you run the predicate at function exit. And if you think about it that way, a whole lot of things just get answered for you. So at that point, like if you know it's a closure, why don't just write it like a closure, like a lambda, basically, that has to return Boolean so you can omit the return, just like requires expressions do. The return value has to go somewhere. Oh, wait, we've got this thing called function arguments. We could put the return expression, like the return value through there, but we don't need to specify its type because auto-ref is what you always want for that one. So we're kind of driven towards the syntax for abbreviated lambdas that Barry Revson proposed a while ago and got rejected by EWG for lack of useful applications of the syntax. Turns out we now have a useful application for that syntax. And I hope that we get somewhere with that. Unfortunately, the contract study group, for good reason, is not exactly thrilled about waiting for EWG to mull over abbreviated lambdas before we pass contracts. So we have problems, basically.
Okay.
Fortunately, with regards to C is actually passing lambdas very close, very soon, I believe. They don't have closures, but they are inner functions that you can just pass to qsort or whatever they have, right? And they use roughly the same syntax as in C++ because somebody, looked at it and said, this seems good. So if we pass something that looks like lambdas, C might very well adopt it as well. And that means that C and C++ can share contracts and headers, and that would be wonderful.
Yeah, that sounds great.
But yeah, that's kind of what we're hoping to achieve there. It is not going to make C++ 23.
I was going to say, it sounds like the soonest that's going to show up is C++ 26. And honestly, abbreviated lambdas coming because of contracts, that's news to me. So that would be I know you don't want to wait for it, but I would absolutely love Barry's paper to be able to be brought back to life and go through. So that's like a selling point of contracts for me now.
Yeah, well, speak up. I think people need some cajoling.
All right. Well, Gašper, it's been great having you on the show today. Thank you so much for telling us about deducing this.
Well, it's been a pleasure.
Thanks for coming on.
Yeah. See you some other day. Bye.